Hello students, welcome to Saurav Sir's classes. This video is Number System Part 5 and in this video we will learn about the digital number systems. There are various number systems used in digital representation. The most common number systems are binary, octal, hexadecimal and decimal. Decimal and hexadecimal. They are the common systems. Binary system has base 2, octal has base 8, decimal has base 10 and hexadecimal has base 16. Now these base tells us the number of distinct symbols. Number of distinct symbols. For example, in binary system there are only two distinct symbols, 0 and 1. In octal we have 8 distinct symbols, namely 0, 1, 2, 3, 4, 5, 6, 7. In decimal, we have 10 distinct symbols, 0 to 9. In hexadecimal system, we have 16 unique symbols, namely 1 to 9 and A to F. Next is conversion of decimal numbers into another. Now to convert any decimal number into any system with base n, we divide the number successively by n. We divide the number successively by n. That is, first we will divide the number with n, then we will divide the quotient obtained in the first step by n and successively. For example, suppose we have to convert 35 base 10 into base 3. So we will divide 35 by 3. The quotient would be 11 and remainder would be 2. Then we will divide 11 by 3. The quotient would be 3 and remainder would be 2. Then we will divide 3 by 3. The quotient would be 1 and the remainder would be 0. Then we will divide 1 by 3. The quotient would be 0 and remainder would be 1. So as we can see here, we are continuing till our quotient becomes 0. And these are the remainders obtained. The last one is the most significant digit. Most significant digit, and will be written in the leftmost, that is written 1, then 0, then 2 and 2. And the first remainder is the least significant digit, and it will be the rightmost digit. So 35 base 10 is equals to 1022 base 3. Next is conversion of binary system into decimal. Now, binary system is also known as positional value system. Binary system is also known as positional value system, where each binary digit has its own value or weight expressed as a power of 2. For example, the number 1101.0101 can be represented as following: 1101.0101. The position values would be 2 raised to the power 0, 2 raised to the power 1, 2 square, 2 cube. This is 2 raised to the power minus 1, 2 raised to the power minus 2, 2 raised to the power minus 3, and 2 raised to the power minus 4. And to convert it into decimal representation, we will multiply the digits with their position values. So it would be equals to 2 cube into 1 plus 2 square into 1 plus 2 into 0 into 2 raised to the power 0 into 1 plus 0 into 2 raised to the power minus 1 plus 1 into 1 into 2 raised to the power minus 2 into 0 into 2 raised to the power minus 3 into 1 into 2 raised to the power minus 4, which is equals to 8 plus 4 plus 0 plus 1 plus 0 plus 0.25 plus 0 plus 0.0625, which is equals to, if we add them, we will get 13.3125. So 1101.0101 base 2 is equals to 13.3125 base 10. Octal numbers are similar to binary number system. Here we have 8 unique symbols as 0, 1, 2, 3, 4, 5, 6 and 7, and each digit has its own value or weight expressed. So weight would be power of 8. So if we have the number 324.01, that will be represented as 32401, and the positional values would be equals to 8 raised to the power 0, 8 raised to the power 1, 8 raised to the power 2, 8 raised to the power minus 1, 8 raised to the power minus 2. So the decimal equivalence of 324.01 is equals to 3 into 8 square plus 2 into 8 raised to the power 1 plus 4 into 8 raised to the power 0 plus 0 into 8 raised to the power minus 1 plus 2 plus 1 into 8 raised to the power minus 2, which is equals to, this is equals to 192 plus 16 plus 4 plus 0 plus 0.015625, which is equals to 212.015625. Next is hexadecimal number system. It has base which is equals to 16, so it uses 16 unique symbols that are 1, 2, 3, 4, 5, 6, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and A, B, C, D, E and F. Thus we have 1 of base 10 is equals to 1 of base 16, 2 of base 10 is equals to 2 of base 16, so on till 9 of base 10 is equals to 9 of base 16. Now 10 of base 10 is equals to a of base 16. 11 of base 10 is equals to b of base 16, so on till 15 of base 10 is equals to f of base 16. So when we convert 725 of decimal system to hexadecimal, we will do it as follow. We will divide it by 16, 725. The quotient would be 45 and remainder would be 5. Then we divide it again by 16. The quotient is 2 and remainder is 13. Now since we know that 1310 is equals to d on the base of 16, so it is d, and when we divide it by 16 again, we get quotient 0 and remainder as 2. So 725 in decimal system is written as 2d5 in hexadecimal system. Next is conversion of decimal fraction into a number system with base n. Here we multiply successively the decimal fraction by the radix or the base or radix, which is our n, and write down all the integral values. We write down all the integral values in order. Now suppose for example we have to convert 0.875 base 10 to binary. Then we will multiply it by 2. So 2 into 0.875, which is equals to 1.750. Here the integral value is 1, so integral part is 1. Now we will multiply the decimal part, which is 0.750. We will multiply it by 2 again and we will get the result as 1.5. Here the interior part is 1, so we again write 1, and then we will multiply 2 into 0.5, which is equals to 1.0. Here the integral value is 1 and we can see that we have no decimal value, so we will stop it here and we will have 0.875, that is the decimal in decimal system, will be equals to 0.111. It is in binary system. Similarly, if we want to convert this decimal 0.825 with base 10 into octal system, then we multiply the decimal part, which is 825 into 8. We get it as 6.6. So integral part is 6. Next we will multiply 8 into 0.6, which is equals to 4.8. So integral part is 4. Next we will multiply 8 into 0.8, which is equals to 6.4. So we again get 6 and 4 is the decimal part, so we multiply 8 into 0.4, which is equals to 3.2. So we take 3 and next we will multiply 8 into 0.2, which is equals to 1.6. So we get 1. Then again 8 into 0.6, which is equals to 4.8. So we have 4. Now here we can see that it is a recurring number, so it will not stop. So here we will write up to only 5 figures. So 0.825 base 10 is equals to 0.64631 base 8. Next, suppose we have to convert a number which has both integer and binary parts, like suppose 38.21, which is in the decimal system, and we have to convert it into binary system. So first we will convert the integral part, which will be done as following. So we will divide it by 2, we will get the remainder, quotient and remainder, then we will divide it by 2 again, then we will get the quotient as remainder as 9 and 1, then we will divide it by 2 again, we will get the quotient and remainder as this, then we will divide it by 2 again, we will get quotient and remainder like this, then 2 again, we will get quotient 1, remainder 0. When we will divide it by 2, we will get quotient 0, remainder 1. So the integral part is 38 base 10 is equals to 1001102, and now we will convert the fractional part, which is 2 into 0.21, which is equals to 0.42, so it's 0. Now 2 into 0.42 is equals to 0.84, again 0. Now 2 into 0.84 is equals to 1.68, so integral part is 1. Now 2 into 68 is equals to 0.68, which is equals to 1.36, again 1. Now 2 into 0.36 is equals to 0.72, again 0. It will further continue, but we are only taking up to 5 points, so the answer would be 100,110.00110 base 2. Next is conversion between octal system and binary system. For this conversion, the following table will help in quick conversion, where the octal digits 0, 1, 2, 3, 4, 5, 6, 7 have following binary equivalent. So suppose we have to convert a number, say 273, then its binary equivalent would be 2's binary equivalent is 0, 1, 0, 7's binary equivalent is 1, 1, 1, and 3's binary equivalent is 0, 1, 1. So its binary equivalent is 0, 1, 0, 1, 1, 1, 0, 1, 1. This is its binary equivalent. Similarly, if we have to convert a binary into octal, suppose we have to convert 100. Now suppose we have to convert this number into octal, so we will take the triplets. The first triplet is 100, next is 011, 011, then it is 001, 001, and then we only have 1. So here we will add 2 more 0 in the left to make it a triplet. So it would be like this. Now 001 is 1, 011 is 3, again 001 is 1, 1. So its octal equivalent is 1131 base 8. Next is the conversion of hexadecimal to decimal. Now suppose the hexadecimal number be 3C8.08. We have to convert this to decimal. So this is equals to 3 into 16 square plus c into 16 plus 8 into 16 raised to the power 0 plus 0 into 16 raised to the power minus 1 and plus 8 into 16 raised to the power minus 2. Now we know that C16 is equals to 12, 10. So we will have 3 into 16 square plus 12 into 16 plus 8 plus 8 into 16 raised to the power minus 2, which is equals to 768 plus 192 plus 8 plus 0.03125, which is equals to 968.03125. So this is its decimal equivalence.